In the spring of 2022, astronomers pointed the most powerful telescope ever built at a patch of sky so empty that older observatories had looked at it and found almost nothing. No bright stars, no nearby galaxies, no obvious reason to look there at all. Just a small, unremarkable window into the dark. The image that came back didn't show emptiness. It showed thousands of galaxies, structures so distant their light had been traveling toward us since before the Earth existed. And buried among them, something that had no business being there. Something that has forced researchers to go back to the equations and ask a question nobody expected to be asking in the 21st century. What exactly is the universe made of? To understand why this matters, you have to go back to April 1995. The Hubble Space Telescope, which had only recently been repaired after its infamous blurry mirror was corrected, was pointed at a tiny region of sky near the handle of the Big Dipper. The patch was chosen specifically because it appeared to contain almost nothing. No bright stars, no known galaxies, just blank space. The telescope stared at that patch for 10 consecutive days, accumulating light from the faintest possible sources. When the image was processed and released, astronomers were stunned. That tiny window, covering an area smaller than a grain of sand held at arm's length, contained over 3,000 galaxies. Some of them so distant their light had left before our sun had even formed. The Hubble Deep Field became one of the most important images in the history of science, not because of what it showed, but because of what it implied. The universe was not mostly empty. It was mostly full. Every patch of blank sky, every dark corner between the stars, was a corridor stretching back billions of years toward the beginning of everything. That image reset how cosmologists thought about the universe, and it set a precedent that would define how astronomy was done for the next 3 decades. When you don't know what's out there, you point your best instrument at the dark, and you wait. The James Webb Space Telescope launched on Christmas Day, 2021, carrying 30 years of engineering ambition into an orbit 1.5 million kilometers from Earth. It was built to do what Hubble could not. Where Hubble saw primarily invisible light, Webb was designed to detect infrared radiation, light that has been stretched by the expansion of the universe itself. The most distant objects in the cosmos are receding from us so fast that their light gets redshifted out of the visible spectrum entirely, shifting into wavelengths the human eye cannot detect and that Hubble could barely register. Webb's 6.5-meter gold-plated mirror, nearly 3 times the diameter of Hubble's, was designed to collect that infrared light with a sensitivity the field had never had before. Its stated mission was ambitious. Look back to the first few 100 million years after the Big Bang. Find the earliest galaxies. Understand how they formed, how quickly they grew, and whether our models of cosmic structure could survive contact with actual data from the dawn of time. The scientific community was cautiously optimistic. The standard model of cosmology, built over decades and refined through hundreds of observations, predicted what the early universe should look like. Small, chaotic, dim proto-galaxies slowly assembling in the gravitational scaffolding of dark matter. A universe in its infancy, messy and immature. Webb would see that infancy firsthand, or so the expectation went. On July 11, 2022, President Biden stood in the East Room of the White House and unveiled the first Webb Deep Field image to the world. The image covered a patch of sky about the size of a grain of sand held at arm's length. It was packed with thousands of galaxies. Their light bent and stretched into arcs by the gravity of a foreground galaxy cluster called SMACS 0723, a phenomenon called gravitational lensing that acts like a natural magnifying glass amplifying light from objects even further behind it. Scientists had seen gravitational lensing before. What they had not seen was this level of detail, this depth, this resolution at these distances. In the days that followed, the Webb team released 4 additional images as part of the telescope's first science package. Each one was extraordinary, but it was the data embedded in those images, the spectroscopic measurements, the distance calculations, the mass estimates that began to generate a quieter and more persistent form of alarm among researchers who knew what the numbers were supposed to say. Within weeks of Webb's first observations becoming available to the broader scientific community, a pattern began to emerge that nobody had predicted. The early universe, as Webb saw it, was not populated with small, dim, disorganized proto-galaxies. It contained mature, massive, well-structured galaxies that had no right to exist at that point in cosmic history. One of the first researchers to quantify the problem was Mike Boylan Colchin, an astronomer at the University of Texas at Austin. His team ran the numbers on 6 of the earliest and most massive galaxy candidates in Webb's initial data. What they found, published in Nature Astronomy in 2023, was that these galaxies were pushing against the absolute limits of what the Standard Model permitted. The Standard Model of cosmology assumes that galaxies grow gradually, accumulating mass over billions of years as gas cools, collapses under gravity, and forms stars. In a typical region of space, only about 10% of available gas ever actually converts into stars. The rest is too hot, too turbulent, or too disrupted by radiation from existing stars to collapse. These early galaxies appeared to be running at 100% efficiency, every available atom converting into stellar mass with no waste, no delay, no normal physics. Boylan Colchin described the situation plainly. If these galaxies are as massive as they appear, he said, they challenge our understanding of how the universe works at a fundamental level. That statement came from a peer-reviewed paper, not a press release. In cosmology, that distinction matters. The initial reaction from much of the community was skepticism, which is the correct response. Extraordinary claims require extraordinary evidence. The first Webb data was preliminary. Distance estimates had wide margins of error. Some galaxies that appeared ancient might turn out to be closer and brighter than they looked. Spectroscopic follow-up observations, which measure the precise redshift of a galaxy and pin down its true distance, would sort out the real anomalies from the statistical noise. Those follow-up observations arrived through 2023 and into 2024. They did not resolve the problem. They deepened it. A study led by Ivo Labbé at Swinburne University of Technology, published in Nature in early 2023, identified 6 massive galaxy candidates at redshifts between 7 and 10, corresponding to a period just 500 to 800 million years after the Big Bang. Spectroscopic confirmation of several of these objects placed them exactly where the photometric estimates had suggested. The galaxies were real. They were where they appeared to be. And they were too large to exist under the Standard Model's predictions by a significant margin. Labbé's team calculated that the combined stellar mass of these 6 galaxies exceeded what the Standard Model predicted should exist in their entire observable region of the early universe. Not in a handful of galaxies, in the entire region. The universe had apparently assembled more mass into stars in its first billion years than our best model said was possible in that same time frame. That is not an anomaly you can explain away with better calibration. Then came a complication that seemed, briefly, to offer a way out. In mid-2024, a team led by Catherine Suess, a graduate researcher at the University of Texas, re-examined many of the apparently overmassive early galaxies and found that a specific population of them, compact, red objects quickly nicknamed little red dots, were being inflated in apparent mass by a source nobody had fully accounted for. These galaxies hosted active black holes at their centers, black holes that were rapidly consuming surrounding gas. The friction from all that infalling material generated enormous heat, which radiated outward as intense light. From billions of light-years away, through Webb's cameras, a galaxy with an extremely active black hole looks almost identical to a galaxy with 10 times more stars than it actually contains. The telescope measures brightness. Brightness is usually a reliable proxy for stellar mass. In these cases, the black hole was mimicking the light output of billions of additional stars that didn't exist, inflating the galaxy's apparent size like a floodlight taped to a candle. When the little red dots were removed from the sample, a portion of the tension relaxed. Stephen Finkelstein, a senior researcher involved in the analysis, said directly that there was no crisis in terms of the standard cosmological model, at least not from the galaxy mass problem alone. It was a genuine and important correction. But it was not the end of the story, because even after removing every galaxy contaminated by active black hole emission, roughly twice as many massive early galaxies remained as the standard model predicted. Not enough to break the model, enough to bend it. And the bending was about to get worse. In late 2023, Webb's science team announced a new deep field program. Building on the legacy of Hubble's original blank sky stares, they selected several regions of sky with minimal foreground contamination and began accumulating exposure time far beyond what the first public images had used. One of these programs, the JWST Advanced Deep Extragalactic Survey, known as JADES, combined observations from Webb's near-infrared camera and its near-infrared spectrograph across a region centered on the original Hubble ultra-deep field. It was, in effect, Webb looking at the same blank patch of sky Hubble had looked at in 1995 and again in 2004, but with instruments capable of seeing roughly 100 times fainter. The JADES program accumulated more than 32 days of total exposure time across multiple observing windows. When the data was processed and the catalog was assembled, it contained more than 45,000 individual sources. 45,000 galaxies in a patch of sky smaller than a thumbnail held at arm's length. The sheer number was remarkable, but it was the specific objects at the far edge of that catalog that generated the most urgent scientific conversations. Objects so distant, so faint, and so structurally unexpected that they have no clean explanation under any current model of how the universe evolved. Among the faintest objects in the JADES catalog were sources detected at redshifts above 12, and in some cases approaching or exceeding 14. A redshift of 14 corresponds to a look-back time of roughly 13.5 billion years. The universe is approximately 13.8 billion years old. These objects, if confirmed, existed when the universe was less than 300 million years old. For context, 300 million years sounds like a long time. In cosmological terms, it is barely a heartbeat. It is the equivalent of a human being fully grown, muscular, and structurally complete 1 week after conception. The standard model does not prohibit galaxies from beginning to form that early, but it constrains how much mass they can accumulate. The gravitational scaffolding of dark matter halos, which galaxies grow inside, takes time to assemble. You cannot build a large structure before the foundation has had time to solidify. Several of the extreme redshift objects in the JADES catalog are not consistent with that constraint. A team led by Kevin Hainline at the University of Arizona published a spectroscopic analysis in 2024 confirming the distances of several JADES sources at redshifts above 11 with high confidence. One object in the dataset, provisionally designated JADES-GS-Z14-0, was confirmed at a redshift of 14.32, making it the most distant spectroscopically confirmed galaxy ever observed at the time of publication. Its light left when the universe was approximately 290 million years old, and it is not a faint smudge. It is a galaxy with significant stellar mass, ongoing star formation, and detectable oxygen emission. Oxygen is a heavy element. It is produced inside stars and released when those stars die in supernova explosions. The presence of detectable oxygen in a galaxy that existed 290 million years after the Big Bang means that at least one previous generation of stars had already lived and died inside it. Formed, burned through their fuel, exploded, and seeded the galaxy with heavy elements, all within the first 300 million years of cosmic history. That is not impossible under the Standard Model, but it requires star formation to have begun almost immediately after the first hydrogen clouds began to cool, with an efficiency that current simulations struggle to reproduce. To understand why this creates a genuine problem, you need to understand what the Standard Model actually predicts about the first galaxies. The leading framework is called lambda CDM, shorthand for a universe dominated by a cosmological constant, which represents dark energy and cold dark matter. In this model, dark matter, which does not emit light and interacts only through gravity, forms the first structures after the Big Bang. It clumps together into halos. Gas falls into those halos, cools, and forms stars. Small structures merge into larger ones over time. It is a bottom-up process. The universe builds from small to large, from simple to complex. Lambda CDM has been extraordinarily successful. It predicts the large-scale structure of the universe, the distribution of galaxy clusters, the temperature fluctuations in the cosmic microwave background, the abundance of hydrogen and helium produced in the first few minutes after the Big Bang. No competing model matches its track record across so many independent observations. But it was built and calibrated using data from the relatively nearby universe, from galaxies whose light took only a few billion years to reach us. Webb is showing us something it was never calibrated against: the universe at its very beginning. And at that extreme distance and that extreme age, some of its predictions are not holding. Priyamvada Natarajan, a theoretical astrophysicist at Yale University, described the situation in 2023 with careful precision. The Webb findings, she said, are suggesting that the formation of the first stars and galaxies was more efficient and more rapid than any current model predicted. That is not a statement that the model is wrong. It is a statement that something in the model is incomplete. The question is what? Several possibilities are being actively investigated. The first is the simplest. The initial mass function, the distribution of star sizes in early galaxies, may have been different in the young universe. Modern star-forming regions produce a mix of small, medium, and large stars. In the early universe, the gas was hotter, denser, and lacked the heavy elements that help it fragment into smaller clumps. It is possible that the first generation of stars was dominated by extremely massive objects, 100 or more times the mass of the Sun, that burned fast, produced enormous amounts of light, and seeded their galaxies with heavy elements on a compressed timeline. If early galaxies were filled with these massive stars, they would appear far more luminous per unit of stellar mass than galaxies today, making them look more massive than they truly were. This would relax the tension between observations and predictions without requiring new physics. The second possibility is more disruptive. Some theorists have proposed modifications to dark matter itself. The cold dark matter model assumes dark matter particles are slow-moving and interact only gravitationally, clumping into smooth halos on all scales. But several lines of evidence, including the distribution of dwarf galaxies around larger ones and the internal structure of dark matter halos, have hinted for years that cold dark matter may not behave exactly as modeled on small scales. Alternative models, including warm dark matter, in which particles move faster and resist clumping on small scales, and wave dark matter, in which quantum effects create a minimum halo size, make different predictions about early galaxy formation. Some of these alternatives allow for faster, more efficient galaxy assembly in the very early universe, which would be more consistent with what Webb is seeing. A third possibility, the most speculative, but the one generating the most theoretical excitement, involves early dark energy, a hypothetical burst of additional expansion energy that existed in the first few 100,000 years after the Big Bang, then decayed and vanished. This idea was first proposed as a potential solution to the Hubble tension, the unresolved disagreement between two independent measurements of how fast the universe is currently expanding. If early dark energy existed, it would have altered the conditions of the primordial universe just enough to change how quickly the first structures could form. It would not break everything else the Standard Model gets right, but it would require adding a new ingredient to the equations that has never been directly detected and for which there is currently no independent confirmation. Here is what makes this moment in cosmology genuinely significant, not just as a puzzle for specialists, but as a statement about where human understanding stands. The universe is approximately 13.8 billion years old. For most of that history, we have had no direct observations. Everything we know about the first billion years was inferred, extrapolated backward from what we could see in the nearby universe using the equations of the Standard Model. Webb is the first instrument capable of actually looking at that period, not modeling it, looking at it. And what it is finding does not fully match the extrapolation. That is not a failure of science. It is science working exactly as it should. A model makes a prediction. An observation tests that prediction. The observation finds a discrepancy. Scientists investigate the discrepancy until they understand it. What is unusual about this particular moment is the scale of what might need to change. If the discrepancy turns out to require modifications to dark matter, those modifications ripple through the entire structure of the Standard Model. Dark matter is not one piece of the picture. It is the gravitational skeleton on which everything else hangs. It determines where galaxies form, how they cluster, what the large-scale structure of the universe looks like on the biggest scales. You cannot change its fundamental properties without changing almost every prediction the model makes downstream. And if early dark energy turns out to be real, it means the first chapter of cosmic history. The era we have described with the most confidence, the era from which we extrapolated everything else, was more complicated than we knew. There is something specific about finding unexpected things in empty space, not in the vicinity of a known object, not near a star or a galaxy or a structure that might hint at something hidden. In the blank. In the part of the sky that was chosen precisely because there was nothing there to contaminate the signal. Hubble looked at nothing and found thousands of galaxies. Webb looked at the same nothing, deeper, and found galaxies that arrived before they should have, carrying heavy elements forged in stars that lived and died before the model says they had time to exist. The universe hid its strangest contents in the places we were most confident were empty. That is either a coincidence or it is a pattern. And in cosmology, when a pattern appears in the data, you don't dismiss it. You follow it, carefully, with better instruments and more precise measurements and the slow, grinding machinery of peer review and replication. Astronomers are already doing that. The JADES program is ongoing. The Roman Space Telescope, scheduled for launch in 2027, will survey a volume of space 100 times larger than Webb's deep fields, providing a statistical sample that could settle several of these questions or open entirely new ones. The Euclid mission is already mapping the geometry of the universe on scales that will constrain dark energy models with unprecedented precision. The answers are coming. They will take years. They will arrive in the form of papers that most people will never read, written in a language most people will never learn, describing a universe that most people will never fully picture. But the shape of those answers is already visible in the data. The universe is older than we thought in some ways, faster in others, stranger in the places we assumed were most understood. That blank patch of sky near the Big Dipper, the one Hubble stared at for 10 days in 1995 because it seemed to contain nothing worth looking at, turned out to contain everything. Webb pointed at the same nothing and found something even emptiness couldn't hide. Whatever is out there, it is not waiting for us to be ready. It is already in the data. We just have to be willing to follow it wherever it goes. Thanks for watching, and I'll see you in the next one.